So basically, reversible reactions are the ones that go either way. That they can go from the reactant side, that we usually call reactant side, and they can go to the product side, or they can go back to the reaction side, which basically means that either side can act as a reactant. So the left side can be a reactant if it's going forward, and the backward, when it's happening in the backward direction, the product will be acting as a reactant. So when ammonia particles over here, when they collide with each other, they produce reactant. And when reactants like nitrogen and hydrogen, when they collide with each other, they produce ammonia. Not every collision will be useful. Not every collision will produce what we're looking for. So what must they have when they're colliding for the reaction to actually occur? What must they do?
सर इस रिएक्शन को occur करने के लिए conditions क्या है?
Okay, sure. इसकी conditions तो different होती जाएंगी. My question is, when two particles are colliding, is it always the case that they react, or do they have some certain thing that they must have before they start to collide? Is every collision going to give us a result?
Or activation energy.
Activation energy, very good. So basically, we are looking for activation energy. If two particles collide and they don't have activation energy, it is not possible that their collision will be successful. Their collision will not yield any useful results for us. वो collide करेंगे, इधर उधर चले जाएंगे, they won't produce it. But if they have enough kinetic energy, if they have the activation energy, they will collide and they will produce reactant. Okay. So reversible reaction is the one that goes either way. And because of that, it's important for us to understand what factors make it go in either direction. And secondly, what factors we can change to control which side is produced more and which side is produced less. Because let's face it, if you are somebody who's creating ammonia and you own a factory that does that, you don't want ammonia to produce lesser than you would like. You want to produce as much ammonia as you can in as little time as you want. Now, the thing is, we talked about rates of reaction when we talked about kinetics, and we saw that there were 5 different factors that affected how rates of reaction occurred. So we said that, okay, number of successful collisions per unit time, that is going to tell us which thing will react and which will produce, which will increase the rate of reaction. And we said, okay, temperature is one, because if you give them temperature, they gain kinetic energy and they create successful collisions per unit time. The number is increased, which means reaction rate is increased. Similarly, it said if we have gases and we have pressure applied on them, then it is possible that they will collide faster, the particles, and they will create more successful collisions per unit time. Same surface area, if you have smaller particles, that means their combined surface area is greater. So more successful collisions per unit time. So definitely our rate is going to be increased. Similarly, concentration or amount of particles, which has to do with solutions or even pure particles if we have those. So that will change the number of successful collisions per unit time, and that will then increase the rate of reaction. Lastly, we talked about catalyst, which doesn't really do anything to the particles, but just provides an alternative pathway which has a lower activation energy. Remember this thing, you must talk about lower activation energy. And through that, they increase the rate of successful collisions per unit time, which then affects how fast or slow a reaction happens. 5 factors, same conclusion, that we want more successful collision per unit time. Now that applies to reversible reactions. And it applies to reversible reactions in the sense that not only will nitrogen collide with hydrogen to produce ammonia, and all these factors will affect that, it is also possible that ammonia particles will collide with each other and they will produce nitrogen and hydrogen. They will decompose to do that. And then these factors are also going to be important. So we want to figure out which factor we need to control. Second, we want to figure out the extent to which we can control it without making the process too expensive. And thirdly, we want to figure out that if we cannot control it and if we cannot have an ideal situation, then what is a compromise that we can have? So here's the thing, reversible reactions, basically, this whole thing is a system. And this system right now exists of nitrogen, hydrogen, ammonia, which are all gases. Okay? That means I can give them more temperature, I can give them more pressure, I can increase I can add a catalyst in there, I can increase the concentration, and those four factors will change the rate of reaction in either direction, any direction. But surface area isn't really relevant here because we don't really have a solid here. Okay. Now, if you look at the diagrams of these reactions, the energy profile diagrams, then the reactions usually go like this. For example, this reaction is exothermic in this direction. That means it will start at a certain value, go up, go down, and end at a certain value. This is nitrogen and hydrogen, and this side we have ammonia. So what's happening is that we have this much activation energy, and then the energy is this much energy is released, and we have overall enthalpy change somewhere over here. This is delta H. Now here's the thing, because it's a reversible reaction, then that means that the opposite side can also be used. So this blue arrow tells me the activation energy in the opposite direction. If ammonia was to go and make nitrogen and hydrogen, so this blue one is going to be the opposite direction. And then the delta H is going to be this much. This is the delta H that's going to be. Now you can notice that delta H amount is exactly the same as previous. Red and blue arrows are the same, except the direction is opposite, which means if the reaction is going backward, it will be positive delta H, which means in the backward direction, if this is exothermic in this direction, then it will be endothermic in that direction. Now, what does that mean? That means that in the forward direction, when it's going from nitrogen to ammonia, it's going to release energy. It's going to release kinetic energy, and the temperature is going to go up. On the opposite side, it's going to be endothermic, which means it's going to absorb energy. Endothermic side will mean that it is absorbing energy. Okay, that's one factor. So how does rate of reaction and all the five factors that we have learned, how do they help us identify कैसे इसको control करें? तो उसके लिए we have this principle. The principle is basically called Le Chatlier principle. Actually इसका नाम Le Chatlier Brown principle है, लेकिन usually इसको हम बस Le Chatlier principle कहते हैं. So LCBP or LCP shortened, this is going to tell me how rate of reaction occurs. So LCP is really simple. It says in the most simplest way of explaining it, it simply says that the system tries to undo any change on it. Okay? So that's really simple. Like, it isn't exactly, if you go to Wikipedia or if you go to any other online website to figure out what it is, it's possible that they'll give you a much more detailed concept for this. But at the heart of it, this is what it is, a simplified version. It's saying that these system that you have, right now the system consists of nitrogen, hydrogen, and ammonia. This system tries to undo any change on it once it has achieved equilibrium. तो पहले तो ये समझ लेते हैं कि डायनामिक इक्विलिब्रियम होता क्या है. Dynamic equilibrium is when the rate of forward reaction, okay, so rate of forward reaction is the same as rate of backward reaction. Okay, that means जितनी स्पीड से अमोनिया बन रहा है उतनी स्पीड से ही नाइट्रोजन और हाइड्रोजन भी बन रहे हैं. इसका मतलब ये हुआ कि नाइट्रोजन collides with hydrogen, produces ammonia. That ammonia collides with itself to produce nitrogen and hydrogen back. That's a reversible reaction. But when they start to do that at the same speed, we say that equilibrium has been established. Why would we say that? Because that is when जितना अमोनिया बनेगा उतना ही वापस नाइट्रोजन और हाइड्रोजन में कन्वर्ट हो जाएगा, which means that overall there is not going to be any change in the amount that has been created. जितना बनेगा उतना ही रिवर्स हो जाएगा. Okay, so that stage when the reaction is happening but there is no change in the concentration, no change in the amount, that is called dynamic equilibrium. When you start a reaction, it is possible that usko equilibrium nahi mila, but this reaction will not complete. Usually हम जब ग्राफ करते हैं रिएक्शन को, तो हम कहते हैं कि यहाँ से रिएक्शन स्टार्ट हुआ, चलता चलता यहाँ पे आ गया, and when it becomes a flat line we say reaction is complete, right? But that's the thing, usually in non-reversible reactions when this happens we say that okay, maybe the reactant ran out, maybe this was all that could be made and all that, and the reaction is complete. But in reversible reaction that isn't the case. In reversible reaction is never complete. Reaction just keeps on going and it produces a certain amount that you have, और फिर वो उससे ज्यादा प्रोड्यूस ही नहीं करता, क्योंकि जितना वो प्रोड्यूस करता है उतना रिवर्स हो जाता है. तो रिएक्शन कीप्स ऑन हैपनिंग, reaction is happening, collisions are happening, energy is being used, energy is absorbed and released, bonds are broken and bonds are made, all of that is happening. लेकिन you will not see any change in the concentration, any change in the amount that is produced, because जितना प्रोड्यूस होगा उतना बैकवर्ड चला जाएगा. ये समझ आ गया कि इक्विलिब्रियम क्या होता है? इट्स नॉट ऑलवेज इक्विलिब्रियम. शुरू में आपके पास हो सकता है आपने नाइट्रोजन हाइड्रोजन ऐड किया, अमोनिया है ही नहीं, तो वो आपस में कोलाइड करेंगे, रिएक्शन रिवर्सिबल नहीं होगा, रिएक्शन सीधा चलता जाएगा until you have enough amount of ammonia to start the reversible reaction. So जरूरी नहीं है कि हर रिएक्शन हमेशा से रिवर्सिबल हो. वो जब इक्विलिब्रियम तक पहुंचता है तब जाकर ही you can see the results of that. Okay, so dynamic equilibrium is when the rate of forward reaction, the rate word is important in there, when the rate of forward reaction is the same as the rate of backward reaction. Okay, and the effect of that is that you do not see a change in the concentration and all that. Okay, so we have a system that has achieved equilibrium. Now what? Now it means that even if you try to let the temperature continue, let the pressure control, let whatever you want to do, आपकी अमाउंट ऊपर नीचे नहीं होगी. जितनी अमोनिया बनी है उतनी अमोनिया बनी रहेगी. लेकिन आपने तो फैक्ट्री लगाई थी अमोनिया की. You are trying to produce ammonia. You don't want कि अब जितना बन गया बस बन गया और आपकी फैक्ट्री चल रही है. You don't want that. It's going to cost you money. So what are you going to do? You're going to learn how to control it. You're going to try कि मैं फॉरवर्ड रिएक्शन को इतना तेज कर दूं कि बैकवर्ड वाला उस तक पहुंच ही ना पाए. Okay, so that way what do we say? We say that you are trying to push the equilibrium forward. So when we want the forward side to be faster than the backward, we say that we want to push the equilibrium forward, or we say that the shift the equilibrium forward, or shift the equilibrium to the right. क्योंकि right side पर आपके products. So how do we do that? So there are three factors that help us determine. पहली चीज आपने जहन में ये रखनी है कि अमोनिया या जो भी रिएक्ट कर रहे हैं उस पे कैटलिस्ट का इफेक्ट नहीं होगा इक्विलिब्रियम पे, उससे सरफेस एरिया का इफेक्ट नहीं होगा इक्विलिब्रियम पे. ओके, दैट इज बिकॉज डायनामिक इक्विलिब्रियम में फॉरवर्ड बैकवर्ड करने में कैटलिस्ट का रोल क्या है? Catalyst lowers the activation energy. Now pay attention to the graph here. Let's suppose the catalyst here is lowering the activation energy, and this is the new activation energy that we have. Now this is a reduced activation energy, but if you notice, not only has the green side reduced the activation energy, the blue side has also reduced its activation energy, which means that the reaction is going to occur faster in both directions. Now you have added a catalyst, good, the reaction is going to be faster, लेकिन इससे इक्विलिब्रियम का फर्क नहीं पड़ा. जितना तेज वो फॉरवर्ड में हुआ उतना ही तेज वो बैकवर्ड में भी होगा. All right, so that's the thing. Catalyst, why does catalyst not affect dynamic equilibrium? Because it reduces the activation energy of both sides. So जितना तेजी से वो फॉरवर्ड हो रहा है उतनी तेजी से वापस भी आ रहा है, इक्विलिब्रियम को फर्क नहीं पड़ेगा. Similarly, surface area में it doesn't really affect because it's not like particles are going to lump together to create a bigger piece. आपने पाउडर बना दिया बस ठीक है, बना दिया तो बना दिया. It doesn't affect the equilibrium or the rate of forward and backward reaction. Individually वो दोनों rates बढ़ जाएंगे, लेकिन equilibrium पे फर्क नहीं आएगा. Okay? So that's something you have to understand. The catalyst and surface area are not relevant to reversible reactions equilibrium. They are relevant to just the rate. आप पाउडर यूज करते हैं, रेट तेज हो जाएगा. If you have a solid, let's say, then the reaction will be faster in both directions, but it won't mean that the equilibrium is changed. It's not. Alright, so what actually then affects equilibrium? The most important factor is temperature. What does temperature do? And temperature is important because of two reasons that we'll study. Temperature क्या करता है? Temperature means you're giving them kinetic energy. So this means you're giving them kinetic energy. You increase the temperature, you have gave them kinetic energy. That means they're going to collide. And what will they do when they collide? They will break bonds and they will create new bonds. Bond breaking is endothermic. हमने ये पढ़ा था. So bond breaking is endothermic. What does it do to energy? It absorbs energy. Bond making is exothermic. What does it do to the energy? It releases energy. Okay? That means if you're giving them more energy, then that means they already have extra energy. Then they will try to undo it. Remember LCP? System tries to undo any change on it once it has achieved equilibrium. The system is at equilibrium. You give it more energy, which means you increase the temperature. It will try to undo it, which means it will try to absorb that energy. Absorb करेगा तो क्या करेगा? Endothermic side पे जाएगा. So what have you done? You have increased the equilibrium, you have shifted it to the endothermic side. In this particular example, it will go to the left. इसका मतलब क्या हुआ? इसका मतलब ये हुआ कि आपने ये पर्टिकुलर रिएक्शन करवाना है, तो अगर तो आपने अमोनिया को तोड़ के नाइट्रोजन और हाइड्रोजन क्रिएट करने हैं, then that is the best decision to do. बहुत ज्यादा टेम्परेचर पे इसको रिएक्शन को करें. But if you want to create ammonia, then you let the reaction create energy. Let the reaction release energy. आप अगर टेम्परेचर बढ़ाएंगे तो वो उसको absorb करने के चक्कर में बैकवर्ड जाना शुरू हो जाएगा. So ideal conditions for ammonia here will be you have very low temperature. इतना लो टेम्परेचर है कि वो उसको रिलीज करना शुरू कर देता है एनर्जी, और जब वो रिलीज करेगा वो एक्सोथर्मिक साइड पे जाएगा. और अगर आपने नाइट्रोजन और हाइड्रोजन क्रिएट करने हैं, यू वांट टू ब्रेक अमोनिया, यू वांट इट टू गो इन द बैकवर्ड डायरेक्शन, यू वांट टू शिफ्ट द इक्विलिब्रियम लेफ्ट. बहुत सारे तरीके हैं बात करने के. इफ यू वांट टू डू दैट, देन यू डू द रिएक्शन एट हाई टेम्परेचर, and that way it will absorb that energy and it will convert to the backward side. But what's the problem with that? There's an added thing here. Temperature also affects, obviously, it affects kinetic energy. And kinetic energy affects the speed of reaction, the speed with which they collide. तो अगर आप बहुत कम टेम्परेचर कर दोगे तो speeds of collision will be reduced. And it is possible कि वो एक्टिवेशन एनर्जी से भी नीचे चले जाए. तो आपने टेम्परेचर, एक खास लेवल का टेम्परेचर हर रिएक्शन को चाहिए, अदरवाइज उसके पास एक्टिवेशन एनर्जी नहीं होगी, जितना मर्जी कोलाइड करे रिएक्शन हो ही नहीं पाएगा. So that is why we have to keep a compromising attitude here. The compromise is that temperature is kept high to have a higher rate of reaction. Higher rate of reaction से क्या होगा? Time बचेगा. You will be able to produce more things in this less amount of time. But the problem with this is that पहले आप बहुत कम टेम्परेचर पे ज्यादा अमोनिया क्रिएट कर सकते थे. हाँ, उसको टाइम ज्यादा लग रहा था, मे बी 1 हफ्ते में प्रोड्यूस हो रहा था. अब आप उससे कम प्रोड्यूस करेंगे लेकिन जल्दी कर लेंगे. So it is a compromise. It reduces the yield. if the reaction is exothermic, having a low temperature will be more favorable, will be more useful for yield, the amount of production. But we do a compromise, we still keep the reaction high, temperature high, because we want to have a higher rate of reaction. ठीक है, हम रेट ऑफ रिएक्शन फिर भी ज्यादा रखने के लिए कि अच्छा चलो कम प्रोड्यूस हो जाए लेकिन प्रोड्यूस जल्दी हो जाए, अमाउंट जहाँ पे 100 kg प्रोड्यूस होना है वहां पे 30 kg प्रोड्यूस हो जाए लेकिन जल्दी प्रोड्यूस हो जाए. टू सेव दैट टाइम वी डू अ कॉम्प्रोमाइज. So does everybody understand where the idea of compromise comes from? How is this related to equilibrium and the shift in equilibrium? Does everybody understand that?
सर
जी.
सर इक्विलिब्रियम शिफ्ट की मुझे समझ नहीं है कि अगर जैसे टेम्परेचर ज़्यादा होगा तो किधर शिफ्ट होगा या कम होगा तो किधर
बहुत सिंपल सा है. आपने देखते हैं कि मेरा रिएक्शन एक्सोथर्मिक है कि एंडोथर्मिक. अगर रिएक्शन एंडोथर्मिक है तो वो अब्सॉर्ब करेगा एनर्जी, तो आप उसको टेम्परेचर देंगे जिसका मतलब है आपने उसे काइनेटिक एनर्जी दी है, वो उस काइनेटिक एनर्जी को अब्सॉर्ब करता रहेगा, रिएक्शन चलता रहेगा, वो एंडोथर्मिक साइड पे चलता रहेगा. आपका रिएक्शन है एक्सोथर्मिक, दैट मींस आप रिएक्शन को एनर्जी कम दें, वो खुद एनर्जी रिलीज करेगा. ठीक है, सो वो एक्सोथर्मिक रिएक्शन के लिए बेहतर है कि हम उसे कम टेम्परेचर पे करें और एंडो के लिए बेहतर है कि हम उसे हाई टेम्परेचर पे करें. ठीक है, द प्रॉब्लम इज कि अगर हम बहुत कम टेम्परेचर कर देते हैं तो काइनेटिक एनर्जी कम हो जाती है, which means now the temperature will basically, the rate of reaction will be very less, which means our reaction is going to be really really slow. We don't want that, तो हम उसको फिर भी compromise कर लेते हैं. So here's a diagram that I want you to see to understand what equilibrium would look like. ये देखें. If I'm trying to find the rate of reaction, you can see that the rate of forward reaction is reducing and the rate of backward reaction is increasing, and there comes a time when the both rates are equal. And when that happens, we say that the reaction has achieved equilibrium. इसका मतलब ये नहीं है कि उसके अंदर इक्वल अमाउंट्स हैं. That's exactly not what it means. मैं ये नहीं कह रहा कि उसमें जितनी नाइट्रोजन है उतनी अमोनिया है. That's not what I'm saying. What I'm saying is that the speed at which ammonia is created is the same speed at which nitrogen is created in this example. Okay, so that is basically equilibrium. And how do you figure out what side you should go in? You control the factors that affect it. So पहला factor जो हमने देखा था वो temperature है. Temperature means it's related to two things: the speed of collisions and the energy of particles for bond breaking and bond making. So if you give more energy, reaction will absorb that extra energy, तो endothermic side पे जाएगा. If you cool it down, the reaction will release extra energy, which means it will go into the exothermic side. So you want to go, if you want it to go in the exothermic side, let it happen at a low temperature. If you want it to happen for the endothermic side, if you're favoring that, then let it happen at a high temperature ताकि वो energy absorb करता रहे. But remember that having a low temperature will reduce the activation, will possibly not give them enough activation energy as well. तो reaction हो ही नहीं पाएगा. Okay, so using temperature has two effects and you have to consider both of them. So that was the role of temperature. Second, we have the role of pressure. Pressure only affects gases. Just remember that. Okay, it cannot affect others. So I'll give you the same example again: nitrogen plus 3 hydrogen producing ammonia. These are all gases, right? Pressure is force per unit area, right? Our physics में पढ़ते हैं. Where's that force coming from? It's the forces of collisions. It is when these particles collide with each other and the walls of containers. Remember, walls of container are also important. Otherwise, some pressure check नहीं कर सकते. So when that happens, these particles collide with walls of container, and number of collisions per unit time per unit area, all of that helps us figure out what the pressure is. जहां पर पार्टिकल ज्यादा होंगे उसका प्रेशर ज्यादा होगा ऑब्वियसली. अब यहाँ पे आप देखो, on the left side we have 4 moles of gas. On the right side, we have 2 moles of gas. It's not moles, it's basically fraction. अगर मैं यहाँ पे देखना चाहूँ, the ratio in which these are, इसके इस साइड पे 4 है, उस साइड पे 2 है, और ये 2 वाली साइड से 4 की तरफ बन रहे हैं और 4 वाली साइड से 2 की तरफ बन रहे हैं. Remember, I'm not saying कि वो 2 मोल हैं, I'm just saying the ratio is 2 to 4, which means the pressure of the product is half of the pressure of the reactant. क्योंकि रिएक्टेंट ज्यादा है ना, उसके मोल ज्यादा हैं, तो मतलब उसके पार्टिकल्स ज्यादा हैं, दैट मींस उनकी पोल्यूशन ज्यादा है, दैट मींस उनका प्रेशर कंट्रीब्यूशन ज्यादा है. दिस इज कॉल्ड पार्शियल प्रेशर. In this particular example, reactants have a higher partial pressure and products have a lower partial pressure. ठीक है, इसका मतलब ये है कि when we increase the pressure, then that puts a higher force on the 4 वाली side because उसके particles ज्यादा हैं, उन पे ज्यादा pressure लगेगा. ठीक है, they will collide more and they will go into the forward side जहां पर pressure कम हो जाएगा because उसका 2 की तरफ partial pressure कम है ना, तो वो उस तरफ जाने की कोशिश करेंगे. तो the reaction favors the forward side, equilibrium favors the forward side if you do this reaction at high pressure. Similarly, if you reduce the pressure, then the collisions will favor the left hand side because they will try to create extra pressure now. Remember LCP, reaction tries to undo any change of it. When you reduce the pressure, it's going to go into the left side because that is where there is a higher partial pressure. Partial pressure depends on moles. We have higher number of gaseous moles on the left side, so उधर pressure ज्यादा है. आपने pressure कम किया, वो उसको ज्यादा करने के लिए left को आएगा. आपने pressure ज्यादा किया, वो उसको कम करने के लिए right को जाएगा. Any more explanation of this isn't required in O levels. In A levels we do, but not in O levels or IGCSE even. So just remember that wherever you have more gaseous moles, that is the side that will be favored if you lower the pressure. And wherever you have less gaseous moles, that is the side that will be preferred or that will be favored if you have higher pressure. So that is how gases are affected. Remember that this is related to gases only. Solids and liquids do not play a part in this. All right? So that's one. Now let's say this reaction was reversible. Let's suppose this was. If I increase the pressure, which side will it go in? My question is that if I increase the pressure in this reaction, and let's suppose this is a reversible reaction, which side will be favored?
जहाँ पर इक्विलिब्रियम शिफ्ट होगा वो आप कहना चाह रहे हैं?
I'm sorry?
सर जहाँ पर प्रेशर कम होगा वहाँ पर ही जाएगा.
Yes, that's exactly what I've told you. जहां पर आपने प्रेशर बढ़ा दिया तो it will go to the side that has lower partial pressure. Okay? And if you have higher pressure, it will go to the side with lower partial pressure, ना? तो यहाँ पे आप देखो, आप gaseous moles को देखो. Here you have one gaseous mole and here you have two gaseous moles. So when I increase the pressure, it goes to this side. When I decrease the pressure, it goes to this side. It's always the opposite of what you're doing. You increase the pressure, it goes to the side with lower partial pressure, which means backward. When you increase the pressure, when you decrease the pressure, it goes to the side with higher partial pressure, ताकि pressure ज़्यादा हो जाए, so it goes to the right. Okay, and that is where the equilibrium shifts. All right. Lastly, we have concentration or amount of particles. That is really simple.
सर
Yes.
सर ये ऊपर वाली इक्वेशन में दोनों जगह 2 नहीं है सर, कार्बन के साथ भी, तो सर दोनों में सेम
That's the thing. Carbon is a solid, so it doesn't affect. It's not affected by equilibrium. ठीक है? उसकी contribution नहीं है pressure के लिहाज से.
सर फिर गैस के अंदर होगा ना सर प्रेशर?
Yes, it's only the gaseous moles that matter. Okay, lastly we have concentration or amount of particles. अब concentration में आपने ये देखना होता है that you are basically increasing the number of particles that you have, which means the concentration will affect rate of reaction directly. More particles means more collisions, or that means more collisions mean more reaction. तो अगर मैं let's suppose ये एक reaction करवा रहा हूँ और मेरे पास बहुत ज़्यादा ऑक्सीजन है, and mind you, I do not mean that I'm running out of sulfur dioxide. I'm just saying that I have a lot of oxygen. Then that oxygen particles are going to collide more. इनका रिएक्शन ज्यादा होगा और जब इनका रिएक्शन ज्यादा होगा वो दूसरी तरफ चला जाएगा इक्विलिब्रियम. सो अगर आप सल्फर डाइऑक्साइड अगर ये चीज आप ज्यादा कर देते हैं तो ये कोलाइड भी ज्यादा करेगी, व्हिच मींस द रिएक्शन गोज फॉरवर्ड. अगर आप का कंटेनर है उसमें रिएक्शन हो रहा है, you reduce the amount of sulfur trioxide that is in there. आप किसी तरह टैप खोलते हो, sulfur trioxide को बाहर निकाल देते हो. Then what that would mean is that you have decreased the amount of sulfur trioxide. So obviously the forward side becomes faster, the reaction favors the forward side, it produces more sulfur trioxide to achieve equilibrium. So जिस साइड के पार्टिकल्स कम होंगे उस साइड पे वो बनने की कोशिश करेंगे, और जिस साइड पे पार्टिकल्स ज्यादा होंगे उस साइड पे वो कोलाइड ज्यादा करेंगे, वो कम हो जाएंगे. So for concentration and amount it's really simple. जिस चीज से ज्यादा होंगे उतना ही ज्यादा उसका रेट ऑफ रिएक्शन होगा और उतना ही ऑपोजिट साइड पे आपका इक्विलिब्रियम जाएगा. So reversible reactions are all explainable just by looking at LCP. That system tries to undo any change on it. और आपने बस समझना है कि वो चेंज कैसे इफेक्ट करती है. वो टेम्परेचर की चेंज है तो वो काइनेटिक एनर्जी इफेक्ट करेगी, which means they will absorb more if it is endothermic and they will release more if it is exothermic. तो आप टेम्परेचर बढ़ाते हो तो वो absorb करता है, एंडो की तरफ चला जाता है. आप टेम्परेचर कम करते हो वो रिलीज करता है, एक्सो की तरफ चला जाता है. Pressure affects partial pressure. So जिस साइड के moles गैस के ज्यादा होंगे they will be affected more. So if you increase pressure it goes to the side with lesser gaseous moles, and if you decrease the pressure it goes to the side with higher gaseous moles to increase the pressure. And concentration affects the number of particles. So if you have higher number of particles they will collide more per unit time, increasing the rate and going into the opposite direction. One idea of compromise that when you increase the if you decrease it too little, that too much, then that would mean the activation energy is also not there. So we keep the temperature high to get a higher rate of reaction, to save time, even at the cost of yield, even when we cannot produce as much as we would like, but we still save time and we keep the reaction fast. Sure, then I'll explain it again. So temperature is related to kinetic energy, and kinetic energy changes the speed of things. So that means the first and direct effect of temperature is on rate of reaction. The rate of either side, forward and backward, both of those sides, they will collide more if you have higher temperature, and they will produce more of the product, more reaction will happen. The rate will be higher because there is more collision per unit time. Similarly, if you reduce the temperature, then there is less number of collision. And not just that, if you reduce the temperature, then it is possible that particles won't even have activation energy, which means the reaction हो सकता है कि रुक ही जाए या बहुत स्लो हो जाए. Which is the reason that when this happens, the temperature is usually a compromise. We compromise on temperature. We keep it high even if it doesn't give us the good yield. Now let's see how it affects reversible reaction. For that, we have to understand how energy affects endothermic and exothermic. When bonds are broken, the reaction is endothermic, okay? And that means it's going to absorb energy. Any kinetic energy that they have, it's going to absorb some. And when the reaction is exothermic, then that means bond making is happening and there is a release of energy. So ये हमारी background है, ये हमारी theory है. Now, how does temperature affect reversible reaction, or how does it affect equilibrium? So here's the thing. Equilibrium में आपके पास जो भी रिएक्शन है उसकी एक साइड एंडोथर्मिक होती है, एक साइड एक्सोथर्मिक होती है. आपके पास कोई भी रिएक्शन है, आपके पास ये रिएक्शन है ऐसा, लेट्स सपोज, तो इसका मतलब है forward side is endothermic and backward side is exothermic. Which side will be favored depends on what you're doing. If you increase the temperature, then the equilibrium will try to reduce it, जिसका मतलब है कि उसे absorb करनी है energy, which means कि वो endothermic की side पे जाएगा. And if you decrease the temperature, that means उसको energy ज़्यादा करनी है, release करनी है, temperature को increase करने के लिए, तो वो exothermic की तरफ जाएगा. And that's simple. That's how it affects reversible reactions or equilibrium. All right.